ionization. Dr. Pokmelnik, who's the Russian physicist who developed this technology back in the 80s and early 90s, wound up in Mexico basically because Russian rockets were being used to propel Mexican satellites into orbit. And there was some scientific exchange between those two countries. And as a result, the Mexican government embraced the technology that Pokmelnik was working on of artificially ionizing the atmosphere to try to induce precipitation. And the result is he did wind up in Mexico, and in 1996, the state government of Sonora in Mexico ordered the installation of 2 stations. The results, both in terms of precipitation and in terms of the water levels of the reservoir systems around the operational area of the stations, were apparently very good. But Mexico being what it is, the government ran out of funds for 1997. There was no operation. And then in 98 they got some funds and set up 1 station. And again, the results appear to be impressive enough so that the neighboring state of Durango ordered 3 stations installed in 1999, and to this point there are some 15 stations in about 6 states running artificial ionization stations, and the federal government has embraced the program and it's going to be funding it. However, what the Mexicans have done is they've only recorded precipitation data. And because they've recorded precipitation data, because of the high variability of precipitation data, 5 years isn't really enough to prove anything, so we don't have any kind of, we have statistical indicators that make it strong enough and interesting enough that, we're willing to move forward. What I'd like to do is I'd like to outline some of the current research that was used for us to be able to develop a hypothesis as to how this technology works. And then I'd like to describe the experiment that we have planned later this year, which will try to test this hypothesis. The basic premise of the body of current research is that ionization, and we're talking about cosmic ray ionization, is a factor in determining the population of cloud condensation nuclei and ice-forming nuclei. The first event that sparked the research of cosmic ray ionization and how it interacts with cloud physics was produced in 1997 by a couple of Danish scientists, which correlated the cloud cover existing on Earth with the intensity of cosmic ray flux. That was later confirmed in the UK, but only for cloud cover that is less than 3 kilometers above the surface. And then in this country, in fact in this city, at the University of California, San Diego, a couple of physicists observed that the correlation was positive for low cloud cover, 0 for cloud cover above 3 kilometers, and sometimes even negative correlation. It all starts with nucleation. The traditional theories of homogeneous binary nucleation and homogeneous ternary nucleation simply were not enough to explain the nucleation observed in the atmosphere. And not until kinetic nucleation, which is ion-induced and ion-mediated nucleation, was taken into consideration, were the levels of nucleation comparable to what actually happens in the real world. Now, most cosmic ray ions that are produced are lost due to ion-ion recombination. About an equal amount of ions are positive and negative, and so they recombine. And only a small portion of those ions are available to charge aerosol. But when those do charge aerosol, then those charged aerosols are very active in several ways. One of them is that they are very actively scavenged at the cloud clear air border by water droplets in clouds. And charged evaporation nuclei, this is an aerosol that has lost its water to evaporation, retains all of the water all of the charge that the water leaves when it evaporates. It also retains some chemical and organic compounds that the water acquired during its growth process. These evaporation aerosol become very efficient ice-forming nuclei. And as they get to the border of the cloud, they are, according to the author, electroscavenged. When you have an ion that is combining with molecules, you will have a charged molecular cluster that simulations have shown that it will preferentially achieve stable and observable sizes. And this molecular cluster will grow and will have lifetime in the days of in a matter of hours and even days. And some models that were run determined that an increase in the ionization rate will also increase the long-term duration of these molecular clusters. The conclusion is really that that ionization has to be linked to cloud processes, to the microphysics of clouds. And if ionization is linked to the microphysics of clouds, it's also linked to weather. There are three processes that have been theoretically established for cosmic ray ionization. First of all, it's aerosol formation by lowering the nucleation barriers. Two, it's changing the rates in which aerosols grow due to coagulation, but also due to condensation. And three, ionization is associated to the removal of particles by water droplets at the surface of clouds. So, lower cloud cover primarily correlated to cosmic ray ionization. Ion losses primarily due to ion-ion recombination, but some to aerosol attachment. Charged aerosols achieve stability in lifetime in the order of days, hours, days, or weeks. And cosmic ray ionization is linked to aerosol formation and aerosol growth. And aerosols can grow to become CCN or ice-forming nuclei. The hypothesis that we developed is that if we take a generator and through corona effect liberate ions into the atmosphere, these artificially generated ions are going to behave in much the same way as cosmic ray ionization behaves. But there are some differences. The ions that are produced artificially, corona effect ions, are hygroscopic. And the losses that we are going to have for corona effect ions, since the ions are unipolar, are not going to be ion-ion recombination. That's going to be pretty much zero. So all of the ions that are produced are going to be available to charge aerosol. And ions attaching to aerosol will produce long-lived, stable particles that through thermals, through turbulence, through Brownian movement, will be able to reach the PBL and beyond. Now, ion-mediated nucleation produce condensation nuclei that can grow into cloud condensation nuclei, and there will be other aerosols that contain pollution materials, and those aerosols that contain pollution materials, when they are charged, are going to be more efficiently scavenged and deposed to the ground, and that's going to have a cleansing effect on the atmosphere. So, in a nutshell, the hypothesis is corona effect ions work just like cosmic ray ions, but they're unipolar, so they're not lost through recombination. They're hygroscopic, and they're effective catalyzer in all of the processes of the aerosol. The model is that you have ions produced either by cosmic rays or by corona effect. They very, very quickly form ion clusters in a matter of seconds or even fractions of a second. These ion clusters then, going to fast track, which is the charged part, are going to form very stable charged clusters, and they will grow to become nanoparticles in the order of 3 to 10 nanometers. Then they are going to go into the Aitken range of aerosol and grow to the point where they're CCN, and then beyond grow to charged droplets, and finally to precipitation. Just an interesting side note. The authors of this diagram are talking about corona effect ions as one of the factors in the overall weather model, but if you'll notice, the corona effect ions that they're talking about are corona effect ions produced by power transmission lines. Now, power transmission lines are transmitting alternating current, and therefore most of those ions are lost to by recombination, ion-ion recombination. So there are very, very small amount of ions that are in fact corona effect ions, and in spite of it being so small, they have considered this as a factor in their model. I'd like to talk a little bit about the experiment that we're going to be conducting a little later this year to test this hypothesis that I was talking about. We're going to have an ionization station that has a central tower and it has some peripheral posts, and that's only the support structure for the antenna, which is going to be a very thin wire antenna that goes around the peripheral posts and radially to the central tower, and this thin wire is completely isolated electrically from all of these posts. There's going to be a generator that's going to be pumping a very high voltage into that thin wire, producing corona and liberating ions into the atmosphere. The station is going to be installed just south of the city of Laredo, Texas, and because of the prevailing summer winds, we estimate that the ellipse on this map is going to be more or less our operational area, and we have defined a spot which is going to be a witness area in the city of Freer, Texas. The objective is going to be to regulate the number of CCN that we have in the atmosphere. And what we're actually going to do is we're going to try to find the resonant values so that we can produce a condition or the conditions for giant aerosol that will produce the giant droplet that will translate to precipitation. We're going to be measuring precipitation, both actual to historical value as well as operational witness. But since precipitation data is such a high variability, has such a high variability, we're also going to be measuring particle deposition, and we're going to be measuring atmospheric charge and atmospheric particle counts. And these are going to be particles that are CCN and beyond, 100 nanometers and larger. And we're going to be doing so on a ground grid that is specified over there, approximately. But we're also going to be measuring at different altitudes. And we're going to actually take a plane and have the plane do a flight grid at different altitudes to see if we can determine the volume of operation or the volume of influence of the station. So it's an exciting opportunity. Measurements like this were only made once before, and that was by Vonnegut in the late 50s. We'll have the opportunity to make these measurements, and we should have results and analysis within 18 months.
I still want to continue this right now because that's why we're here, actually. Dave, you were doing ground. Go ahead, Dave.
Well, Vonnegut and Moore tried this over 40 years ago, and I don't recall, and you did not remind us of the results, but if they were, they had some measurements which seemed they measured the electric field, but why were they not continued?
Yeah, as far as I know, they did measure some things, particularly atmospheric charge. And what they found is they found atmospheric charge as far as 10 kilometers away from their generating wire. Their generating wire was a single strand wire, and their generator was a relatively low power generator. It wasn't a very high power generator. And they discontinued because if the charge is only going to be, if the field of influence is only going to be 10 kilometers away from the station, it's just not practical. It has to be greater than that. And I believe that that's the reason that they discontinued because they were going to continue these experiments in Illinois. The original ones were being done in the Southwest, but they were going to continue in Illinois, and they never did.